Hello, in this module we will discuss the standard Gaussian random variable, which is also called the standard normal random variable. A standard normal random variable is a normal random variable with mean 0 and variance unity. A standard normal random variable also gives rise to the Gaussian-Q function. The Gaussian-Q function plays an important role in computing the tail probabilities, which is frequently required to compute the bit error rate or probability of error for various digital modulation techniques. We will also in this module introduce the central limit theorem formally. So let us begin. Let x be a standard normal or Gaussian random variable. That means x is distributed normally with mean 0 and variance unity. The PDF of the probability density function of the standard normal random variable then is given by fxx equal to 1 over root 2 pi e to the power minus x square by 2 for all x in the interval minus infinity to plus infinity. Let us also sketch it. It is the bell-shaped curve which is centered at the origin because mean is 0. In this case, notice that it is also an even function. In general, the Gaussian random variable has a distribution or density function which is not even, though symmetric about the mean value. But when mean is 0, as in case of a standard normal random variable, the PDF also becomes an even function. Let us now look at what the CDF of this function would be. The cumulative distribution function of a standard normal random variable, capital F x x. By definition, it is related to the PDF as its integration. So integration minus infinity to x fx some dummy variable tau d tau, which in this case becomes equal to integration minus infinity to x, and fx is 1 over root 2 pi e to the power minus tau square by 2 d tau. As you can see from here that suppose this is some point x, then we are actually computing the area under the PDF curve from minus infinity up to the point x. This is a standard occurrence and has a special notation. Instead of writing capital Fx, we frequently write this standard integral in the form of phi function, capital Phi of x, which is called the standard normal CDF or the CDF of a standard normal random variable. More often than not, we are interested in computing the probability that a given standard normal random variable is greater than or equal to small x. That is, we are interested in computing the tail probability. This is called the tail probability that is the probability that the random variable x takes on values greater than or equal to small x. This clearly can be computed by integrating, as we can write here, the probability of x greater than equal to small x can be computed by integrating the PDF curve from x to infinity 1 over root 2 pi e to the power minus tau square by 2 d tau. This function bears a special name, what we call the Gaussian-Q function. It is defined as q of x, and clearly this is equal to 1 minus phi of x, because phi of x is the integration minus infinity to x, the area marked by these black lines, and the q function gives this area. The total area is unity, fxx being the PDF, the total area is unity, and therefore q of x is 1 minus phi of x. We normally use the q function in all our computations. So let us formally write once again the probability x greater than equal to small x, where capital X is the standard normal random variable. It is given by the q function, Gaussian q function q of x, which is defined as 1 over root 2 pi integration x to infinity e to the power minus some dummy variable tau square by 2 t tau. So let us box it. This relation must be memorized. It may be noted that this integral cannot be expressed in a closed form. However, the values of this integral has been tabulated extensively for a large range of x, and therefore they can be used in computations. The question then arises that can we compute the CDF and therefore the tail probabilities of a general Gaussian random variable with mean not necessarily mu 0 and the variance not necessarily 1. Can we use the q function there? The answer is yes, and let us see the procedure. So let us consider a general Gaussian random variable. By general we mean that the random variable x is distributed normally with mean sum mu and variance sigma square. In that case, as we know, the PDF is given by small fx x equal to 1 over sigma root 2 pi e to the power minus half x minus mu by sigma squared for x lying in the interval minus infinity to infinity. The corresponding CDF which is denoted by capital F can be written as integration minus infinity to x 1 over sigma root 2 pi into e to the power minus half some dummy variable tau minus mu by sigma squared d tau. Now let us make a substitution here. Put tau minus mu by sigma equal to some variable z, which implies that d tau equal to sigma dz, and let us look at the limits as tau varies from minus infinity to x in this integral, z varies from minus infinity to, as you can see from this equation, when tau is minus infinity, z is also minus infinity, and when tau is x, z equal to x minus mu by sigma. So it is x minus mu by sigma. Now with this we can write down, so this implies that the CDF fxx equal to integration minus infinity to x minus mu by sigma 1 over sigma root 2 pi into e to the power minus half. Now tau minus mu by sigma is z, so z squared into d tau is sigma dz. Now sigma and sigma cancel, and we get this is equal to integration minus infinity to x minus mu by sigma 1 over root 2 pi e to the power minus z square by 2 dz, which by definition is the standard normal CDF denoted by phi x. As you can go back and see the definition of phi x. So phi x is simply integration from minus infinity to x 1 over root 2 pi e to the power minus tau square by 2 d tau. Any dummy variable we can use tau or z, whatever. So here we see that it follows this form. So I should write here, it is phi of x minus mu by sigma. So this way the CDF of a general random variable can be expressed in terms of the CDF of the standard normal random variable and the values for which are tabulated extensively. The same can also be expressed in the form of a Q function, because we know that Q of x is 1 minus phi, phi of x equal to 1 minus qx. So this can be written as 1 minus q of x minus mu by sigma. The phi function denotes the CDF, the q function then denotes the complementary CDF or CCDF. Just make a note of that on one side. That phi function gives the CDF, whereas the q function gives the CCDF, the complementary CDF. This first C stands for complementary. Let us now look at the central limit theorem. Broadly, the central limit theorem states that the sum of a large number of independent and identically distributed, in short IID, random variables exhibits a Gaussian distribution regardless of the form of individual density function of the random variables. Formally, let us assume that let x1, x2 and so on up to xn be IID random variables, NIID random variables. Let us define another random variable. Let yi be xi minus mu x upon sigma x, where mu x is the mean of xi's, because all have the identical distribution, so the mean of all the random variables will be same. And similarly, sigma x denotes the standard deviation of all xi's, because all the random variables are identically distributed, so their variance will be same and therefore their standard deviation will be same. Note that this substitution xi minus mu x upon sigma x ensures that the yi has the expectation, the mean value, which is 0, and the variance of yi is equal to 1. In general, it can be shown for any random variable that if the mean of the random variable is subtracted from it, the new random variable will have a 0 mean, and then when it is also divided by the standard deviation, the new random variable will have unity variance. That's very easy to show. Now define another random variable, say Zn, which is equal to 1 over root n summation yi equal to 1 to n. We are adding all the yi's and dividing by root n, which is equivalent to writing 1 over root n summation over all I from 1 to n xi minus mu x upon sigma x, which becomes 1 over sigma x root n summation I equal to 1 to n xi minus n times mu x. Then the central limit theorem states that as n tends to infinity, Zn tends to becoming a normal random variable with mean 0 and variance unity. That is the formal statement of the central limit theorem. It can also be stated as a property of convolution, which says that the convolution of a large number of positive functions is normal. It may be noted that the joint PDF of sum of two random variables is equal to the convolution of the two random variables. In general, when we have a large number of positive functions, identical positive functions, then their convolution leads to a bell-shaped function, which is a normal or a Gaussian random variable. The central limit theorem is central to making the Gaussian random variable so important, because many physically observed phenomena can be modeled as Gaussian distribution, because for many physical phenomena the overall random effect is due to the combined effect of several independent and identical random phenomena, and therefore the central limit theorem holds, and therefore the overall distribution is a Gaussian distribution. A classic example of this is thermal noise in communication receivers, which is the result of several randomly moving electrons in the conductor, but the combined effect is a Gaussian distribution, which makes the analysis of the system very easy. So, in this module we introduce the notion of a standard Gaussian random variable, which is the Gaussian random variable with zero mean and unity variance. We looked at its PDF and CTF. We noted that the tail probability can be computed from the standard normal PDF as Q function, and that any general Gaussian distribution can be expressed in form of Q function, and therefore the tail probabilities can be computed. And finally, we talked about the central limit theorem, which plays a central role in modeling several physical phenomena as the Gaussian random phenomena. So that's all for this module. Thank you.